One of the applications of derivatives is to find the minimum and maximum values of a function. Of course, we could do this just by looking at the graph of a function using a calculator or a software program which would help us visualize graphs. But we're going to take a calculus-based approach to find the minimum and the maximum of a function. So minimum value of a function is the smallest value of a function in its domain I shouldn't say in its domain, or I should simply say on an interval. And maximum value of the function is the largest value of a function on an interval. Now, the reason why I changed the phrasing here from the domain to on an interval is because if we look at a function in its domain, then there could be more than one minimum value. There could be more than one maximum value in the entire domain. So the plural for minimum values is minima, and the plural for maximum values is maxima. And minimum is the lowest a function could get, so it is an extreme. Maximum is the highest a function could get, that is also an extreme. So collectively they are called extreme values, or in a plural form we simply call them extrema. Now there are two types of minima and maxima that one can observe. The first one is called a local minima or maxima, and the other is called the global or absolute minima or maxima. Suppose I have a function of that sort, and let's say that is the domain. I'll go down there. And if you look at this function, it's bumpy, it's going up and down, up and down. And you can see that this is a maximum point that the function attains, but it is a maximum point on a small interval, which would be right here. So that would make this point a local maximum. Same argument applies here. We have a large value, but that particular value is the largest on that shaded interval. So the interval was right here on the x-axis, the interval was right there on the x-axis, so that would also be a local maximum. Now I have a third point here. So on that interval, this point is the highest. So that would correspond to a local maxima. But this maxima is the highest of the other two, or of all three. So this particular value is larger than that one and that one. So this is also the absolute maxima of the function. Now, the minima, that is a small value on an interval along the x-axis. That interval would be that part. So the value that I just sketched is the smallest value on the interval that I shaded, and that would become a local minimum. In a similar manner, if I looked at an interval to the right and left of that point, then that point would also be a local minimum. But the question here is, does it have a global or absolute minimum? It does not, even though the lowest value is right here for the function. We don't call it an absolute maxima, or absolute minima, because this is an endpoint. So we don't typically look for an endpoint and say, okay, that has to be the local minima or the maxima. And in a similar way, we can't consider that also, because that point is also an endpoint. So if I called A, B, C, D, E, then in this picture, A, f of A, C, f of C, E, f of E are local maxima, and E, f of E is an absolute maximum, B, f of B, D, f of D are local minima. And the coordinate B is where the extreme value occurs in the domain of the function, and f of b is the value of the function, or the maximum, or the extreme value. I'll just say value of the function. So the x-coordinate is simply the point where the extrema occurs, and f of b or f of d, f of a, f of c, f of e, those are all the values of the extreme value that we observe. So here are a bunch of theorems that are useful in understanding how we could use calculus to find extreme values, in the sense we've got to find minimum and maximum values of a function. The first theorem is called the extreme value theorem. So suppose we have a continuous function on a closed interval closed in the sense I am including A and B. And let a minimum and maximum occur at some points C and D, then C, D must be in the interval or the open interval A, B. Might seem confusing, but what we're trying to say here is if we have a function, so that is A and that is B, and if we suggest that the function has a minimum and a maximum, if it attains a minimum or a maximum, which in this case there is a local minimum and local maximum, so that's the local minimum, local maximum. Then the C and D must be in the interval A, B. In other words, C and D falls in the interval between A and B. And you've got to keep in mind that we cannot include the endpoints. So, which is why I changed the interval, which was closed right here, including A and B, to an open interval over there, indicating that I'm not including the endpoints A and B in looking at the extreme values. Another important theorem here is Fermat's theorem. What does the theorem state? So if a function, should rather say has a minimum or maximum at x is equal to c, then f prime of c would be equal to 0. That is, the derivative of the function at x is equal to c is 0. Well, we all know the derivative is simply the slope of the tangent line at a given point. So I'm going to draw a tangent line here and there in green, and you can see exactly at C right here and D, the slope is 0. In other words, if I find the derivative of the function at those 2 points, C and D, the derivative will be equal to 0. So what we're saying is if we know that a function has a minimum or a maximum at x is equal to c, then f prime of c has to be 0. There is a caution here though, in the sense the converse is not true. That is, if f prime of c is equal to 0, then it doesn't imply that the function has a minimum or maximum at x is equal to c. That's what we mean by the converse. In other words, the reverse is not true. A good example would be a cubic function and I have x is equal to 0 over there, and I want to draw a tangent line, and if I drew it, it's going to be right there. And the slope of the tangent line at x is equal to 0 is 0, i.e. f prime of 0 equals 0. But look at the picture though. The derivative at x is equal to 0, which is the slope of the tangent line, is 0. But do we see a maximum there? No. Do we see a minimum there? No. It's actually flat. So we don't have a maximum or minimum. So you've got to be careful when we interpret Fermat's theorem. If we have a continuous function and we know that there is a maximum or minimum at a point C, then the derivative at that point has to be 0. But the converse is not true, in the sense that if I know that the derivative at a point is 0, it doesn't imply that there would be a max or min. A very good illustration is right here in this picture of the cubic polynomial. One of the numbers that we use to find, I don't know if I have it later. No, so I should probably summarize it here. So I'm going to delete this page. One of the things that we use to find local minimum and maximum are called critical values or critical numbers. A point is a critical number if, I'll say a point C is a critical number if f prime of C equals 0 or f prime of C doesn't exist. If either of those happens at C, then C is a critical number. And also, another point to notice is that if a function has a local minimum or maximum at x is equal to C, then it is a critical number. Now that goes back to Fermat's theorem, if you think about it.